is Giann. I'm a PhD student at the Sister Research Center, and I'm going to be talking about runtime verification based on firmware specification. And this talk will be basically an introduction to runtime verification. I'm going to be talking about what it is, what it isn't, when to use it, its components, instrumentation and monitor synthesis, what can we verify with it, its relation with the project, and some tools. So let's start with some contextualization, because runtime verification is part of a bigger research field called formal methods. And in the context of values, we're mostly concerned with the verification and validation aspects of our systems. Because of this, I want to contextualize the use of formal methods as another tool for us to use to achieve our goals. With that in mind, I want to start with a quote from Dijkstra that says that program testing can be used to show the presence of bugs, but never to show their absence. And that's when formal methods come into play. The idea is to discover possible flaws by having a holistic perspective of the system instead of sticking with the test cases. On top of that, many safety critical systems nowadays require a combination of formal methods to certain certifications. It's worth mentioning that I'm not saying that you should stop testing your stuff, but to actually combine the tools that make sense to your problem. I'm just going to leave some success stories for those that are interested later in the presentation. And for those who never heard of it or don't really remember anything about it, formal methods are rigorous mathematical techniques that can be used to systematically specify, develop, and verify software and hardware systems. Formal methods are basically divided in two ways of using it: formal specification and formal verification. First one is formal specification, and as the name suggests, it's a way of specifying something, you name it. So let's say we want to develop a motor controller, and although natural language makes it easy to describe a high-level specification of what it should do, it will be probably full of ambiguities. Formal language, on the other hand, are harder for us to digest, for the human eye to digest, but are much more precise. And that's where formal specification shines, because it helps the developer or the engineer to understand the system behavior, and it makes it easier for them to discover flaws, inconsistencies, ambiguities, and incompletenesses. Nowadays, it's supported by many formally defined languages. And next up is formal verification, that goes a step beyond of what formal specification can do. And instead of only specifying, you can actually perform some check-ins about a model or specification that you come up with. It's divided in two groups. First one is static formal verification, and it's performed during design time, in the sense that you don't need any runtime information to perform your verifications. It aims at exhaustively checking every single possible state of to find the trickiest of the corner cases, which could end up being serious threats in the future. To do so, it also requires a lot of computing resources. A good example of use of formal static formal verifications, is formally verifying cryptographic protocols, where you can find possible corner cases that could result in security threats later on. The second one is dynamic form verification, and that's that's what I'm going to talk about in this talk, which is basically focusing on runtime verification. And on the contrary of static form verification, it uses runtime information to perform verifications, but it comes at a price of a limited coverage. Runtime verification analyzes small snapshots of the system behavior to issue fast results, instead of trying to cover everything at once as static form verification does. So recapping, while on the first you have complex specification of the entire system, on the second you focus on checking smaller parts of a system using runtime data. In this, as I said, in this talk, I'll be talking about runtime verification, but later on, José is going to be talking about model checking. So when should you use form verification? It's normally used to complement the cases where static form verification couldn't do what you want, what you wanted it to do. So, for example, in the cases where there is it's just too complex for the current machines to compute anything useful of our models, and that's why formal static verification is known by the problem of state explosion. Sometimes you just don't have the data that you need to perform some verifications. Other times it's just too expensive to wait for verifications to be performed, and then you just attack some specific cases using formal runtime verification. And other times, nowadays tools are too limited to cover all the assumptions that you need for the real system. I also want to clarify some things that are in the literature. So that's my view of what the terms in the literature mean. Because, for example, sometimes people confuse the two terms. Runtime verification is more than just logging information. That's what runtime monitoring means, just logging information. In our case, runtime verification means checking formal properties of your system using a formal specification, although the two are not really completely dissociated in the literature. Runtime verification is also known as trace analysis and dynamic analysis, for example. It's also important to note that runtime verification does not interfere in the system itself, in the sense that if something goes wrong with the system, the idea is that formal verification only identifies it. If you want to take some action on it, this research field is called runtime enforcement. So let's go with an example. Although it's not the most complex example out there, let's say that you want to use runtime verification on a traffic light. To perform runtime verification, we need some elements, which are the formal parts of it. So runtime verification is composed of events, which are things that are observed in the system, some kind of behavior that is observed in the system. It could be a change of state, some timeout, or some trigger that happens. For example, a light turned red, or a pedestrian pressed the stop button. Traces are sequences or sets of events. For example, we saw that the traffic light went red, it went green, and went yellow. And let's say that's one trace that you observed in your system. Then you have a formal specification, which is a mathematical way of saying what the system should be doing. It can be described using state machines, regular expressions, or temporal logic. And the monitors itself is when you combine the formal specification to monitor the data that we saw over here, the events and traces. This picture over here gives a clear idea of what we saw so far. So we saw that a system exhibits events and traces, and the monitor analyzes it. The thing that I was missing is how we connect the two, and that's when instrumentation comes into play. So basically, what instrumentation does is connect systems and monitors. The way that it does depends on what you want your system to do. So, for example, if you want your monitoring architecture to be fully developed with software, you need to know that you are going to have some kind of computational overhead. If they are hardware units, you need somehow to probe them, and it's also going to incur in overheads in terms of cost, space, and energy consumption. You can also classify monitors in terms of being inline or outline. Inline monitors are the monitors that are placed inside of the application code, and outline monitors are basically monitors that execute independently of the of the monitored application. And because of that, you can achieve a better isolation in terms of temporal aspects and logical aspects. You can also increase parallelism by using outline monitors, but you also have to keep in mind that you somehow have to probe the system to obtain the data, because when you use inline monitors, the monitor is already inside of the code, and it makes it much easier to get information. A classical example of outline monitors is when you have to monitor legacy systems where you cannot change the system itself, but you actually have to use interfaces to be able to get any information out of it. And the last classification is in terms of being offline and online. Since there is not much research nowadays in offline runtime verification, we're just going to focus on online verification, which means that the monitors are running alongside with the system. So there is a spectrum of how tightly coupled the monitors are to the system that ranges from tightly coupled to loosely coupled. And to explain each of these items, I'm just going to come. I just came up with an example where we have a system that has some component called T, and the system is correctly executing its stuff when a action is only performed after a login was performed beforehand. So, for example, in the completely synchronous monitoring, every time there is an event that happens in the system, all tasks are blocked. All tasks are blocked until a monitor can say that something happened or nothing bad happened in the system. So, for example, over here, the component T1 performed a login and nothing bad happened. But in the case of T2, it's trying to perform an action before having done any login beforehand. And that means for this monitor that there was a violation of some formal property. The second case is where instead of blocking the whole system, you only block the components of tasks that are related to the thing that went wrong. Third example is when you have checkpoints. The idea is that the system keeps sending events to the monitor, but the monitor only issues a verdict when both all the tasks that are related to that checkpoint and the monitors are synced up in the same checkpoint. With synchronous monitoring, with synchronous detection, the idea is that you only block the tracks, the tasks or components that are performing tasks that can be problematic. So, for example, when T1 tries to log in is not a problematic action. But when you try to make an action, it can be a problematic action because it's supposed to have the system, the track or the task actually is supposed to perform a login before performing any action. And the last example will be where the system just sends a bunch of events to the monitor. The monitor buffers it, and after some time, it just says if there was a violation or not, based on the traces that it analyzed it. So for monitor synthesis, the idea is that you get your formal specification and turns it into monitors in an automated way. You can do it in two ways. The classical way is where you synthesize a block of code, which is the classical way of doing it, the monolithic way. And more modern approach, you can do it distributedly, where, for example, you generate bits of code that are spread in your system, and they can be either orchestrated, where there's like a single unit orchestrating all the other monitors, or each monitor has its own part, which is the choreographed approach to it. I'm just leaving some tools over here for those that are interested. But Copilot is a very well-known stream-based hard time tool for generating monitors. And I just want to talk about what can we actually verify using runtime monitoring. You can verify actually many things. It's basically up to the tool that you use and why you want to use. For example, event ordering, the correctness of some values, temporal properties. You can also abstract all these things to say that these relate to some safety property or some liveness property. But at the end of the day, you are most likely getting one of these results. It's either true or false, the thing that you analyze. It can also be true, inconclusive, or false, in the sense that the monitor doesn't have enough information to tell you if it's true or not the thing that you want to verify. Or it can also be true, still false, still true, or false, in the sense that at that point where you try to verify something, it was still true, but later it can develop in a false trace, or it can still be true later on. So how do we verify it? The techniques are local quantification, where you put checkpoints in the system, basically saying if you reach that checkpoint, it means that it's good or bad to the system. You can use temporal quantification, where you analyze the temporal ordering of your events. It can either be like relative, saying that one thing has to happen. If one thing happened, there was another thing that happened before it, just like the case that we just saw, where for some action to be performed, there had to be a login beforehand. Or you can actually use absolute values of time. Data quantification is like an extension of the temporal quantification, where on top of having this ordering of the systems, you also analyze how the data changed or didn't change between the occurrence of the two events. And with abstract data specification is where you specify an abstract model of the system, and your runs of the system or your traces and events have to fit in that abstract model. If you want to go to the approaches, I just listed the approaches that are related to the techniques that we just saw. So for example, with assertions, the idea is that you put a statement in your code to check if something is true or not. With pre and post conditions, is that you analyze some properties, some assertions before and after something happened. So it's really common to use pre and post conditions before and after methods to check if whatever happened in that method, if it still complies with the conditions that you set for the pre and post conditions. With the invariant, the idea is that properties must hold at all locations where it is expected to hold. With state machine and process algebra, the idea is that the current run of your program has to be a refinement of another abstract program. With temporal assertions, the idea is to basically reason about, as we said before, the ordering of events. And you also have domain-specific languages where you come up with like complete formal specific language for the thing that you want to verify. Finalizing, the idea is to explain a little bit what's the relation of runtime verification and values. In this context, we want to make sure that form verification of monitor generation is correct, in the sense that we make sure that the properties that you want to verify are actually correctly specified. If they don't specify, if you're not trying to verify something that is unverifiable. We also want to kind of make a popularization of RV, and that's one of the things that we've been working on, in the sense that we are creating a DSL, a domain-specific language, to make it more friendly, make runtime verification methods more friendly to the users. We also want to make sure that whenever you enhance your system with runtime verification aspects, that the monitors don't actually have a negative impact on the safety properties of it. So, for example, we want to make sure that whenever you introduce monitors to a real-time systems, that the monitors do not disrupt the scheduling of it, for example. We've been also playing with the idea of using fault injections to check what the behavior of the monitors would be under unexpected situations. And also with the idea of speeding up the testing of properties with formalism to try to find corner cases that with normal testing you probably wouldn't find it. So the conclusion is that runtime verification is a method for formally verifying properties where we have this timeline of that's the way that you formalize things. So you have your system that it generates events and traces. There was a formal specification of the things that you want to verify. You have the monitor that verifies it for you, and then it gives a verdict saying if the thing that you wanted to know is true or not. It's basically used to complement static formal verification techniques. So it trades the exhaustive search of trying to find every single corner case to a more lightweight way of verifying things, where you just verify limited parts of the system that interest you the most. You can verify many things of it. It's up to you what you want to verify, and also to the available tools. But tool support is actually growing, and I'm just leaving some reference tools for those that are interested later on. I'm just also leaving some references, and time for questions, I guess.